All right, so for this last example, we have a given steam turbine with 80% stage efficiency, which receives 7 MPa and 550 degrees Celsius and exhaust 20 kPa. Determine the quality and exhaust or at exhaust, no? Okay, so we have a turbine. So what basically is happening, we have a turbine here. Okay, and then you have your input, no? So you have 550 and 7 MPa, and then the output is just 20 kPa. Okay, so is the work given? Not really. Only the stage efficiency, no? So the stage efficiency, so you have given a work output, so it is not given, but the stage efficiency, that is also the turbine efficiency, which is 80%, no? Okay, so basically, we will use the stage efficiency to find the actual enthalpy of the output, no? So if this is point 0.1 and this is point 0.2, so the ideal is on the bottom of the denominator. So you have h1 minus h2. For the actual, you have h1 minus h2 prime, no? So this can be found, right, using the typical Rankine cycle, no? So you can find H2 prime given this, no? And the quality at exhaust, meaning why do we need to use H2 prime? Because we are trying to determine the actual, no? Actual quality instead of this, no? So actually we have a solution here. It's not quite correct. No? If the stage efficiency is given, it is automatically understood that you need to find the actual values, no? The actual quality. So, in order to solve for this actual quality, you need to first solve the ideal, no? So if this is the TS diagram, no? So you have the saturation line TS, no? So for isentropic, no, you have from point 1, it's a little bit, I think I'll just make the yeah. So you have this point here, for example, 1 to 2, that is isentropic, but the actual, no, is a little bit deviated to the right, no, the 2 prime, no, the actual. So again, 2 is the ideal, 2 is the actual, no. So in this case, yung 1 to 2 natin is isentropic, no. Okay? Yung 1 to 2 prime, which is the actual, is polytropic, no? Technically. But we can find this using the stage efficiency. So in doing so, we can, or sorry, in trying to solve the H2 prime, we need to find H2 first, no? So H1 can be found. H1 is just using the table 3. For point 2, you can use yes, you can use the given pressure to find HF and HFG and SF and SFG. So we want to find the isentropic version first, no, H2. So you need to find the quality using S1 is equal to S2. So isentropic quality here to find the isentropic enthalpy, no? So this is basically H2. So therefore you can find H2 prime. So you have 0.8, and then H1 is 3530.9 minus H2 prime. So H2 prime is not given. And then you have 3530.9 and then minus H2. That is isentropic. Okay, so you can find H2 prime. Okay, so after finding H2 prime, what you can do is you can already find the quality. So the quality here is still the same formula. No, you can still use this. But instead of H2, you have H2 prime is equal to HF plus X prime HFG, no? So in these cases, we have the actual quality with the actual enthalpy. Okay, so let's solve first the, the actual enthalpy. So just use numerical methods here, no? So minus alpha x 3530.9 minus 22879.7. So you have 2537.94. So 2537.94. Okay, so this is in kilojoule per kilogram, no? Okay, now the next thing is to find the actual quality. So to find actual quality, I think I'll just write this down. So you have 2537.94 minus HF. That's still the same HF, guys, no? So 251.4 divided by HFG. So 2358.3. So X prime. So you have 2537.94 minus 251.4 divided by 2358.3. Yeah. So 96.96, no? So 0.9696. So basically 96.96%. Okay? So this confirms our graph here. As you can see, the more left it is, the more the lesser the quality, no? So x is lower, no? Is lower, x lower. But if it is to the right, x is higher. So the isentropic here process has lower quality, which is 86.43 than the actual, no? So 96.96%. Okay, so that's it. Thank you guys for listening.